Well, hello. Now I'm going to go over the review problems and questions, or some of the review problems and questions in Module 2. I'm on page 69 are the review questions for Chapter 2. And then we'll go over some of the practice problems on page 70. Won't maybe not necessarily all of them, but we'll go over certain of these review questions and review practice problems. On page 69, number 1. What two conditions must be met before you can use the three equations that we derived in this module? You'll remember from the lecture and from the book that there's two basic conditions that have to be met for us to be able to use all of the equations in this chapter 2. And those are, number 1, that the acceleration is constant, and number 2, that all of the motion is in a linear line, or we have linear motion, or it's in a straight line. If the acceleration is not constant, if the acceleration changes, or we're talking about curved motion, we have to use we have to solve the problem in a different way, and we'll talk more about that in future modules. Okay, what is number 2, what is air resistance? How does air resistance affect the acceleration of a falling object? Okay, this it talks about it in the lecture I just did on this videotape. This is one thing I did not talk about this in the lecture I just did. It did talk about it in the question in the text in the chapter. This is really an issue. Air resistance is really a force issue. Well, it's an acceleration issue, but it's essentially it's in my opinion, I think the author should have waited to introduce air resistance for maybe chapter 5 maybe, where he talked about forces. He didn't. He introduced it now. That's okay. We'll still explain it. But basically, in air resistance, if we're talking whenever we talk about air resistance, we have to talk about a drag force. We haven't even defined what a force is yet, but let's talk about it. A drag force, if you think about it, if you jump out of an airplane and say you forget you forget your parachute, which is very unfortunate, but maybe God had your time to go anyway, so maybe it's okay. But we're just talking hypothetical here. You jump out of the jump out of an airplane, you forget your parachute, you start accelerating. The acceleration of gravity is, as we know, minus 9.8 meters per second squared. It's also, we can say 32 feet per second squared. That's, you will accelerate at this rate when you free fall out of an airplane. That means your velocity keeps picking up. It picks up and up and up and up. However, at some point, let me say this. Think of this equation here. The final velocity is equal to the initial velocity plus 2ax. Okay? X is in the vertical direction. Since this is a constant, as this keeps on going up and up and up in a negative sense, or maybe I should say down, it keeps going up and up and up. It keeps increasing, the x increases. Our initial velocity, say, is 0 when you jump out of an airplane. Our final velocity should just keep going up and up and up. As our x increases or decreases down from a plane, the absolute magnitude of the distance increases. Our velocity should continue to increase without bound. Okay, but it doesn't. We know that at some point you reach a terminal velocity. And so at some point your velocity becomes a maximum as you fall down. And that maximum terminal velocity, depending on how fast you is, or how, depending on whether you spread your arms out or what you're wearing, it depends on your drag factor, that it may be over 200 miles an hour or less, or you can alter it tremendously. For instance, if you have a parachute, then hopefully you have a parachute, and you pull your parachute out, here you are, here's your parachute, and you have some ropes, and here's you hanging on to the parachute, and you're dangling down safely. At this point, your terminal velocity here is quite low. You're falling, but here your drag is much more increased because of the parachute, and your terminal velocity is much slower. So slow, in fact, you can safely hit the ground and you won't kill yourself. So the shape that you offer the wind has a lot to do with your drag. Now, what does this drag do? Notice this. What happens is the drag offers a resistance. Essentially, it offers a back acceleration this way. What really happens, and this is, we're getting a little bit ahead of ourselves, but I'm just going to go over this anyway. So bear with me. We have a force of gravity. This acceleration is really because of a force of gravity which acts down. Gravity pulls you down. That force of gravity brings about an acceleration down. Okay? We haven't even talked about this yet. It's not for about chapter 5. We'll talk about this. But since we're talking about drag, we have to introduce this. Because what happens is that when you have drag, you have a parachute, the drag force is a force that's counter to the way you're falling. So in this case, the drag force is a force up. Now, when this drag force equals the force of gravity, then that means that your acceleration becomes 0. So, and by definition, we reach terminal velocity whenever our acceleration, our actual acceleration, becomes 0. Essentially what this means is our velocity goes up, our velocity goes up and up and up, only to a point when our acceleration, think of it this way, goes 0. The acceleration is a final, the acceleration is a change in velocity with the change in time. Okay? Whenever our acceleration becomes 0, because we have this drag force that's causing an upward force opposing gravity, whenever these two forces equal, our acceleration becomes equal to 0. Whenever the acceleration equals 0, our change in velocity becomes 0. We don't change velocity anymore. And at that point, if our change in velocity is 0, then that means that the final velocity and the initial velocity for any time are the same. If these two are the same, that means that the initial velocity equals the final velocity. There's no change in velocity. We have reached terminal velocity. So that's a very long-winded answer to why air resistance brings about a terminal velocity. Okay, let's move on. Number 3, define, or what is the definition of free fall? Free fall goes along with this. In free fall, you're falling according to the acceleration of gravity. There's nothing hindering you, maybe a little bit of air resistance, but basically there's nothing hindering you with the exception of air when you fall. Like when this falls, the acceleration of gravity is pulling this down, and it's in free fall. Okay. Number 4, A very picky physicist says that no object can really experience free fall when falling near the surface of the Earth. Explain why the physicist is technically correct. Well, it has to do with this air resistance. There's always air resistance, and the air resistance will always bring about a limit. It will always limit. It will always essentially limit your acceleration. It will limit your fall. And so there's in the perfect free fall, you're accelerating with gravity, and there's nothing inhibiting your increase of velocity except acceleration of gravity. But we know that air resistance does that. So technically, he is correct. Number 5, even though physicists in question 4 is technically correct, explain why we can still assume that most objects fall near the surface are indeed in free fall. The reason is because in order to reach free fall, you have to fall for thousands of feet before you reach terminal velocity. And who can fall for thousands of feet before they reach terminal velocity? That certainly didn't. That only fell for about 5 feet. So in order to actually experience something other than free fall, you have to pretty much jump out of an airplane. So, and not many people do that. It's probably a good thing too. Number 6, if an object is thrown up into the air, where is it at a zero velocity? When its velocity is 0, what is it? Its acceleration. When you throw something up, if you have initial velocity, as the velocity is 0 at the very peak, that's where the velocity is 0 at the very peak, and then it starts to fall back down. But notice that the acceleration of gravity is always there. Remember back in the lecture we said that actually if you throw this object up, it's in free fall the moment it leaves your hand. The definition of free fall is under nothing but the force of gravity, the acceleration of gravity. Doesn't matter if it has an initial acceleration or not. It's still in free fall. So the acceleration of gravity is a change in velocity with the change in time. The acceleration of gravity, 9.8 meters per second squared, is constant all throughout this travel. In fact, this is what slows it down to 0, and it reverses the direction and sends it back down to the Earth. Okay, number 7. On the moon, gravity is significantly weaker than on Earth. Would you expect the acceleration due to gravity on the moon to be larger or smaller or same compared to the acceleration of gravity on the Earth? Well, you probably know the answer to this. This is why the astronauts could jump really high up on the moon. The acceleration, the moon is a smaller mass. Well, we'll talk about this in chapter 6, I think it is. But basically, you would expect the acceleration on the moon to be smaller than the acceleration of gravity on the Earth, and in fact it is. Number 8, a penny and a feather are put in a long glass tube and all the air is sucked out. While inside the tube, will the feather fall faster or slower or same as a penny? I apologize, I don't have a demonstration of this, but if maybe you've seen one of these demonstrations, you have an evacuated tube where there's a vacuum, you put a penny and a feather in it, they both fall at the same rate, because the reason the feather typically falls slower is because of air resistance. You eliminate the air, you eliminate the resistance, the feather falls as quick as the penny. Okay, number 9. A ball is thrown up at initial speed of 1.2 meters per second. The ball is thrown up, if the ball is caught exactly at the same height from which it was thrown, which is right here, but it's going down, if the ball is caught right at the same distance that it's thrown, what would the velocity be? Well, it will be exactly the final velocity here, right at the same point. This is a symmetric problem. Will be exactly 1.2 meters per second, but in the negative direction. There will be a minus sign is coming back down. So, from the symmetry of the problem, the old adage, what comes up must come down. Not only does what come up must come down, but it must come down at the same velocity, at the same horizontal distance. It must come down at the same velocity from which it was up. I'll leave it as an exercise for the serious student, as they say, to actually prove this mathematically. Should be very easy to prove mathematically. Number 10, suppose you have two balls of equal mass. Although their masses are equal, they are made of two different substances. So maybe the two masses are equal. Maybe one's lead and one's plastic. As a result, the first ball is significantly smaller than the second ball. Which ball has the highest terminal velocity? Okay. Because the terminal velocity is dependent on the shape, the smaller the shape, the less wind resistance there is. It's really related to the surface area. So this will have a higher terminal velocity. This will have a lower terminal velocity because this offers more air resistance to it. So hopefully that's pretty clear. Okay, now we're going to go flip over to page 70, and we're going to go over the practice, some of the practice problems on page 70. Okay. Number 1, an athlete runs at a constant velocity. This is number 1. Constant velocity of 3 meters per second. How far will the athlete travel in 25 minutes? Well, this is very easy. This is just the x equal vt, and he's traveling 25 seconds. This is really a chapter 1 kind of question. You put in 3 meters per second, and he's traveling for 25 minutes. So we put in 25 minutes, and the important thing here is that we multiply, we take care of the units, and we go 1 minute is 60 seconds. And we multiply 3 times 25 times 60, and we'll get the answer, and it's X number of meters. And the answer is 4,500 meters. That's a very easy problem. Okay, number 2, likewise, is quite easy. BMW accelerates from an initial velocity of 0 to a final velocity of 60.0 miles per hour, and it does that in 7.9 seconds. The question is, what is the acceleration? Well, this, again, is really a chapter 1 type of question, but it's easy enough to solve. We just use a definition of the acceleration is the final velocity minus the initial velocity, all divided by time. And this is really a units problem. And I will leave this to you to work out the details, but the final velocity is 60.0. That tells you there's 3 significant figures, minus 0, and this is in miles per hour. divided by 7.9 seconds. And in order to convert this to meaningful units, now you could leave it like this, but really what we need to do is to convert, I would convert, well, you could do it either, the answer doesn't tell you what units you want it in, but what I would tend to do would be to probably convert, to leave it in miles per hour. I would convert this to time, to seconds, convert seconds to hours. So 3,600 seconds equals 1 hour. So if we do this, we end up with 60 divided by 9.7 times 3,600, and you get 2734 miles per hour squared. Now we really need to round off to actually two significant figures, so that will be 2.7 times 10 to the third miles per hour squared. Now that's a suitable unit, but really it would be better to convert it to maybe a feet per second squared. I'll leave that to you to maybe convert that to feet per second squared. Okay, number 3, how far does the BMW travel during this acceleration? Okay, so in other words, it accelerates for 7.9 seconds, but what is the distance? The distance traveled? Well, there's actually a couple ways to handle this. Distance traveled equals the initial velocity times time plus 1/2 AT squared. So one way to do it is we could put in the initial velocity and substitute in the time, and we have what the acceleration is, and so we could solve for the time here. That would certainly be one way to do it. It's a little bit long, but is there another way? Yes, there is. That's one way to do it. The other way to do it would be to use this equation. We know what the initial velocity is. The initial velocity is 60 miles per hour. The final velocity, the initial velocity is 0. The final velocity is 60 miles per hour. We know what the acceleration is, and we can solve for x, for the distance. Okay? That's the second way to do it. There's actually even one more way to do it, and that would be to say that the distance traveled is equal to the average velocity times the time. This is my preferred way to do it because it's so much easier. Because the average velocity is simply the initial velocity plus the final velocity, all divided by 2. And notice how easy that is. It's 30.0 miles per hour. And we know what the time is, so it would simply be 30.0 miles per hour times 7.9 seconds. Okay, notice I have to convert either miles per seconds to hours or vice versa. I'm going to just do it right here. Again, 3,600 seconds equals 1 hour. Notice the seconds cancel out, the hours cancel out, and I'm left with miles, and I get 30 times 7.9 divided by 3,600, or 0.066 miles. And if I multiply that by 5,280 to convert miles into feet, I would get 350, and I round off to two significant figures, 350 feet. So that's how far you would actually travel. Okay, number 5. Okay, a rocket ship blasts off from rest and accelerates accelerates for a distance of 2.0 times 10 to the third yards at an acceleration equal to 9.7 times 10 to the fourth feet per second squared. Okay, so it gives you the distance. Here's the rocket. The rocket blasts off and accelerates for this distance, x, and it also accelerates at that rate. So it travels a certain distance, which is this, and it's accelerating. And the question is, what is the rocket's velocity when it's finished accelerating? So what is its, the initial velocity we assume is 0. The question is, what is the final velocity? Right at the top here. Okay? Well, notice that we don't know anything about time. We don't know anything about time, but we do know this distance. We know this distance traveled. We know this distance traveled, and we know the acceleration. So, what equations can we use? We can't use anything initially right off the bat with time, but we can use this equation. The final velocity squared equals the initial velocity squared plus 2 times acceleration times the distance. Okay, so we know what the distance is. We know x. We know the acceleration. We know that the initial velocity is 0, so we can solve for final velocity. The final velocity is 2ax square root of. So it's a square root of 2 times a times x. So the final velocity is 2a is 9.7 times 10 to the fourth feet per second squared. Now x is in yards, but we need to convert that to convert it to feet. We multiply by 3. 3 feet per yard. Yards cancel out, and that gives us 6.0 times 10 to the third feet. Okay, just multiply by 3. So we get 6.0 times 10 to the third feet square root of, and let's see, according to what I have here, the answer is, I've calculated before, is 3.4 times 10 to the fourth feet per second. Okay? That's question number 5. Okay, question number 6. I think what I'll do is maybe some of these I'll just kind of go over the procedure but not actually solve them. Question number 6. In an amusement park, there's a free fall ride that drops the rider straight down for 30 meters. Sounds kind of fun, actually. What velocity is the ride traveling when it reaches the bottom of this straight drop? So you're up here, and you're strapped in very nicely, and it just straight drop all the way down for 30 meters. The question is, what is the final velocity? The initial velocity, we assume, the initial velocity is 0. Okay, what's the final velocity? Really, this is just a very similar to the previous problem. We don't know what the final velocity is. We know what the initial velocity is, and we know what the acceleration is. That's gravity. Acceleration is simply 9.8 meters per second squared. That's gravity. We know what the distance is, so we can solve for the final velocity. The final velocity, again, is simply the square root of 2ax. I'll leave it to you to just fill in the numbers for the acceleration. Notice the acceleration is a negative number. If this is a negative number here, if we take our datum right here of x equals 0 right here, at this point we have x equals minus 30 meters. So